Hello. Am I audible right now? Okay. So can anyone just confirm, like, could you not listen to any of it, like the previous three questions? Okay. So fine. I will start explaining from the beginning. Okay. Just can you tell me from which part you were not able to listen? So till this question, was it fine? Okay. So you are saying that from the first slide, you could not listen, right? After this question. Okay. Fine. So I will explain again. So this question is fine, right? Which of the following represents analog to digital converter? So the fastest one. So it was the flash type, right? The second is that which of the following ADC is more expensive to build? So I suggested a hint that in any integrated circuit that we design, we have some constraints, right? In terms of area, power, time, and accuracy. So, and these are very much intertwined with each other. Like if you try to optimize for power, like if you want to make a low power circuit, then you will have to go for bigger area, more time, or less accuracy, right? So these all are interdependent on each other. If you want to make higher precision circuit or high accuracy circuit, then you will have to give more power or more time or go for bigger area design. Fine. So there is always some trade-off in whatever design that we make. So building on the first question that I asked, that the flash type ADC is the fastest. So this question says which one is the most expensive to build. So biologically, if flash type ADC is fastest, then it must have some bigger area or it should take more time. So flash ADC, sorry, if it is fastest, it should take more area and it should take more power. Okay. So and in any of the integrated circuit that we design, area is directly proportional to the expense. Okay, because the chip, we're fabricating on a chip, right? So the area is limited. So if your design is big, then it is actually amounting to more cost. So in this case, that's the reason why your flash type ADC is most expensive. Fine. So the next question is that which of the following statement is false? So the first question, it says that dual slope ADC has faster conversion time compared to successive approximation ADC. So this is incorrect. So in dual slope ADC, we have an integrated circuit that integrates the signal, and that takes a lot of time. In successive approximation ADC, we have comparator which are much faster. In second question, in second option, it says the opposite. So that's why it's correct. The third option says that flash type ADC is expensive to design compared to dual slope ADC. So as I suggested earlier, bigger area directly relates to more cost. The last option says that flash type ADC has high resolution compared to dual slope ADC. So this statement is also incorrect. The reason is that the resolution is dependent on the number of comparators you have. Okay. So if you have n comparators, you can go up to 2 power n values, right? And your bit resolution will be V reference by 2 power n. Same is the case for dual slope, but the catch is that the comparators are very big in size as compared to flip-flops. In dual slope, you need to make a counter, and counters are made from flip-flops and these are very much smaller in size as compared to your comparators, which are basically made up of op-amps and all. So these are very much bigger in design. So that's why we have a constraint on the number of bits of flat ADC that we can make. So in general, we make flash type ADC of around 8 bits. Okay. But in case of number of counters, we can go up to 16 bits. So in that case, we can say that dual slope ADC has higher precision. Fine. So D is also incorrect. So here I was explaining the working of different kind of ADCs. So here in SAR block, you have n-bit counter. Depending upon the counter value, there will be a digital to analog converter, which will give you this VA value, and there will be a Vin value, which is your input voltage, okay, which you want to convert from analog to digital. So this comparator compares your VA with Vin. If it is 0, it will give the signal to SAR ADC, which will accordingly update the counter and it will give you a new voltage VA. Fine. So in that way, the comparison will keep on going till you converge to the input voltage value. Okay. So in this case, you can see that. So as I was explaining, it starts from MSB1 and rest zeros, and it will keep on updating. It takes multiple iterations to give the output. So that's the reason it is not the fastest ADC. Fine. But it has one comparator. So as you can see, the comparator is less, and that's why the number of iterations are more. So it takes more time. So there is a trade-off. If we increase the number of comparators, the output will be available instantly in one iteration only. Okay. So that's the logic. We always have this constraint of power, area, time, and accuracy. Fine. So just again, am I still audible? Fine. So the next type of ADC is the dual slope ADC. So in this case, here you have this integrator circuit that whatever input that you give, it keeps on integrating with time. Then you have a comparator circuit. Okay. So this is fed to your control logic, and it will keep on counting. So the key, so the V in is basically, this is your T up and this is your T down. Fine. So what happens here is that, so this is the relation that we have for the V input. Okay, if we have to convert, but this is your digital output, right? We want a digital output. So in this case, what we do is that till the time TU is there, we make a counter that keeps on updating. Okay. So this is your counter, right? So you have a signal for TU, and here your counter keeps on updating. Fine. Similarly, for the instance of TD, you have another counter that is counting. And in the end, what you do is that you divide. Fine. So in this case, what happens? You give this input to a T flip-flop, this TU signal, you give this to a T flip-flop, and your counter is made up of T flip-flops, right? So it will keep on counting 0, 0, 0, 0, 0, 1. It will keep on counting. Okay. And the number of flops in your counter will determine the precision, right? Similarly, you will have the TD value as well. Let's call it counter TD. Here you have counter TU, and then you will divide it. Okay, you will have a divider circuit, and then you will get your Vn input. Okay, next moving on to flash type ADC. So in this circuit, the conversion takes time because here it's operating in time, right? So it's integrating, and it takes a lot of time for V out from go to 0 to some peak value, and then it will take some time to go from peak value to 0. Fine. So this takes a lot of time. That's why dual slope ADC is slower as compared to successive approximation ADC. Okay. But still it has only one comparator. So it is by expense point of view similar to successive approximate ADC. Okay. So actually people do not call it successive approximate ADC all the time. They call it SAR ADC. Okay. So in this case, this is your flash type ADC. And you will look something interesting about it, that it has instant output. Okay. Zero iterations, zero time. Apart from what it takes to convert, it will have some minimum conversion time, but that is very small. Okay. So in this case, you have how many comparators? You have 1, 2, 3, 4, 5, 6, 7. So you have 7 comparators. And these comparators are very huge because they are made up of op amps and they're very huge in size. So by huge, I mean that when you will make the layout of this op amp, you will see that they take up a lot of space. Similarly, resistor have some space, and since it takes about n resistors, it will have a lot of area, and that area directly corresponds to cost. Okay. And then you have this priority encoder, which is made up of flops. So this is your flash type ADC. So it takes less time, but it gives you output instantly, and it has more number of comparators. So that's why it is expensive. Fine. So I think it answers. It explains all the 3 questions that I asked previously. Okay. Why it is expensive, and about resolution as well. So resolution, you can see that how many comparators are there. There are 7 comparators. Okay. And this is a 3-bit ADC. Fine. So to make n-bit ADC, how many comparators you would be needing? 2 power n minus 1? Not exactly. You will need 2 power n minus 1. You will need these many comparators. Okay. Which is very much huge. So for that reason, it is very much expensive. So let's move on to the next question. So this is the question. Let X is the input sequence where Z is the output sequence for the state machine shown below. Which of the following options correctly describes the output Z sequence for input sequence X given below? So I will give you some time to think, about 5 minutes to solve this question. So if you want some hint, I can give you. Actually, it does not require any hint. Just to confirm that you know it, the first one represents your input signal and the second one represents your output. So here in this case, the input is X, whereas output is Z. Okay. So I think this will help you to answer this question. So I will start explaining. Hmm. So you are starting from S0 and the path is X equal to 1. So this will follow this path because here this is X and this is Z. Fine. Then X is 0. So this path. Fine. Then it will go again 0. Then 1. Then again 1 and 0 and 0. Okay. So this is the path. So in this path, what are the outputs? So in this case, this is 0, 0, 0, 0, 1, 0, 0. So it should be 4 zeros, 1 double 0. So the answer is D. Okay, so this is clear to everyone. If you have any doubts, let me know how the state machine is functioning. Fine. I am moving on to the next question. So this question says, what is the output of the following circuit for B4 equal to 0, 1, 0, 1, and V reference is 15 volt. So these are the, so by B1, B2, B3, B4, so these are the input bits which are used to program these switches. Okay. So this switch will determine whether the circuit is connected to your op amp or it is connected to ground. Okay. So I will give you 5 minutes to solve this question. In order to solve this question, some basic concepts of op amp is needed. Okay. If it is not visible, this portion is plus and this is minus. This is your V out. The only hint I would like to give you all is that since this portion is grounded, um, there's a concept that since the voltage between these two are so small, we can assume that if this voltage is Vx, then this voltage is also Vx. Okay, approximately. So in this case, this is the ground, Vx equal to 0. So that means that this node is also grounded. I think this will help you to solve this question. I think this is sufficient to solve this question. The rest that you have to do is to use the network analysis. So anyone solved this or close to solving this? So in the lecture slides, I saw that there is a nice formula to solve this question, but actually it is not needed at all. You can figure out using the normal network analysis. So I'm solving this question right now. So there are a couple of things to keep in mind. So as I discussed previously, the voltage difference between these two nodes are very much less. So this is same as Vx, and in this case Vx is grounded. That's why this node is also 0. Okay. Now let's do the circuit analysis. We have a current I1 flowing here, and then we have a current I2. Okay. So by KCL, I1 equal to I2. Now I1 can be written as by KVL. I1 can be written as V reference by R. Let's call it Rx. Okay. And this is Rf. I hope this is visible to everyone. So I1 is Vref by Rx. I2 is V out 0 minus, okay. Yeah, 0 minus V out by Rf. Since these two are equal, we can write V out equal to minus Vref Rf by Rx. Fine. So this is how let's copy this. Hmm. So in the question, this is your Rf, and you have to figure out what will be the Rx. Okay. So Rx will be the resistance that comes in the path from V reference to your out one. Okay. So in this case, you have 0101, right? Or 1010. So this is 1010, which means that this path is connected to V out one. This path is also connected to out one. This is not connected. This is not connected. Okay. Instead, this is connected to another ground. This is also connected to another ground. Fine. So this current that goes, which is, I think, I2 plus I by 2 plus I by 8, which is 5I by 8. That goes here. So this is V out. So V out equal to 5I by 8 into R. V reference equal to. So now this is a little tricky. The reason is that out is also grounded and the other parts are also grounded. So what resistance will Vref look at? So if you make the tree of Vref, it is something similar to this. Vref just to note that this is out one and this is your ground. This is out one and this is your ground. And these two are similar because all of them are grounded. Fine. That is because of this concept. See, out to here is grounded. Okay. Digital ground. For that reason, out one value is also equal to ground. Had your out 2 been suppose 10 millivolt, your out 1 will also be 10 millivolt. It would not be ground anymore. Okay. So now the current I over here, I will be V reference by R equivalent. Okay. So what is the R equivalent value? So this R equivalent will be R. So this will be 2R. This will be R again. This will be 2R. Since these two are parallel again, this will be R. This will be 2R. So R equivalent, if you keep on doing, will finally be R only. So your I is equal to V reference by R. So V out is 5I by 8 into R, which is 5 by 8 IR, which is V reference equal to IR, right? So V out equal to 5 by 8 into V reference. Okay. So in this case, what is the V reference? This is 15 volt. This will be 5 into 15 by 8. So this value comes out to be 9.375. Okay. So initially I said that the V out will be in negative polarity as compared to V ref. So that's why this will be minus 9.375. Okay. So the answer is A.
Sir, have we got 5I by 8, sir?
How we got 5I by 8? Hmm. So we are focused on the current that goes in the out one path. Okay. So this is I by 8 and this is I by 2. Fine. So these current will add up. They will go through out one, through RF to your output. Okay. So hence we got this V out equal to, it will be V out equal to I by 2
Okay.
plus I by 8 into R. Okay. This will be 5I by 8. So moving on to the next question. This is similar to the previous question. I hope you can all do it. So I will give you 5 minutes to solve this question. Did anyone get the answer? So I'm discussing the solution right now. So the current of our interest, I think, are 1, 2, and 3. So that will add up to I by 2 plus I by 4 plus I by 8. Okay. This much into R equal to your V out. And we know V reference equal to IR. So V out equal to I minus I by 8 equal to minus 7 by 8 IR. So this is equal to minus 7 by 8 V reference. 7 by 8 no 15. This comes out to be minus 13.125. Okay. So I hope this is clear to everyone. This question was easier to solve because they already gave you the current division. Otherwise, you would have to find out, which is also very much simple. Depending upon the number of ladder, you can determine that. Okay. So first will always be I by 2, then you will have I by 4, I by 8 in that way. Okay. So moving on to the next question. I think this, yeah. I hope this is visible to everyone. I think this way it's good. So the figure below shows a 3-bit flash ADC circuit. What would be the encoded binary output? D. So your voltage is given 8 volt and input voltage is 4.125. So I will give you 5 minutes to solve this question. So in this question, some concepts of quantization is essential. For example, if I have a wave like this and I have predefined output voltage states, okay, like my reference voltage are like this. So what will happen is that at this point, which is halfway between two states, suppose V0, V1, V2, V3. So this point halfway between so this point lies halfway between V1 and V2. So the all the points before this midpoint will fall to V1 and all the points above this V2 will fall to V2. So the conversion, okay, I think I cannot select it all. So the conversion will look something like this. So this is because of quantization. Okay, let me elaborate. So this is the midline. So it will be, your new signal will be like this. Okay. Quantization. So, and those who do not know about priority encoder, I will explain. So this is similar to decoder. For example, So in case of basic decoder, what will happen is that if this is the input, in case of a encoder, what will happen is that if this is the input, it will give out the uh, binary output corresponding to 3. Fine. But in case of parity encoder, what will happen is that if you give this, then it will give you like this. If it is like this one, it will give you corresponding to 4. Okay. So it only cares. So what priority encoder will look is that it will start from the MSB. It will start from the MSB. It will keep on looking for the first one. Okay. So here it encounters 0, then 0, 0, 0. And here at the third position, it encounters a 1. Okay. So what it does is that it gives you the output corresponding to the binary of the third position. Okay. And then it does not care about what lies after that one. So that's why I have mentioned X over here. Okay. So I think I should discuss the solution. Has anybody got the solution for this? Okay, so let's discuss. Hmm.
So which one is MSB and LSB, sir, in the comparators?
So in this decoder, this is your MSB and this is your LSB.
Sir,
Is it
every
fine?
time it is like that, sir.
Yes, every time.
Okay.
So we have hmm. So we have input voltage 4.125. This voltage is 8 volt. So this is 8 volt. So this node it's 7V by 8. So this is 7 volt. This is 6 volt, 5 volt, 4, 3, 2, and 1. And then we have ground. So 4.125 VA, VB, V out. So if VA is greater than VB, V out equal to 1. If VA less than VB, V out equal to 0. So that way we have this is 0, this is 0, this is 0, this is 1, this is 1, this is 1, and this is 1. Okay. So this we have fed to your priority encoder, right? So this is your fourth place. And okay, fine. I think this is your LSB. And there is one implicit 0 because your encoder will be 8 to 3 conversion, right? So in that case, this is your fourth position. Fourth position. So the output will be 100. So this is the answer. So is this clear? If you have any doubts, let me know.
Sir, first bit will be always 0, sir. LSB.
Yes, you're talking about this one, right?
Yes, sir.
Yes.
Okay, sir.
So should I proceed to the next question? I hope this is clear. So the next question is that what is the primary advantage of using a milli FSM over a Moore FSM? So we have options: simplicity in design, faster response to input changes, output stability, and reduced state complexity. So let's discuss the solution. So in this case, we have simplicity in design. So I do not think that the milli FSM is simple as compared to Moore FSM, because in Moore FSM, you have input that change your states, and the change in state gives the output. This is your Moore FSM. Whereas in milli, what happens is that input changes your state, and you have some state value and input value which goes into a combinational block, some operational block, and that gives you the output. This is your milli FSM. So it is not simple in design. This is complicated. Second is that faster response to input changes. So in this case, you can see that the input updates the state and then the state updates the output. Here also the input updates the state. State also goes to a combinational block that goes to the output. So that is also not correct because it has more delay in the path. C option says output stability during state transitions. Suppose one FSM I have designed, it has certain number of states. For example, it has 5 states. Suppose it is a 100 detector. Fine. So it will have some number of states. It will look something like this. So if we encode these states, it will be like 00, 01, 10. But the problem is that the 11 state is not utilized at all. Okay. And there is a possibility that because of some glitch, it can go over here. So we have to take care of this. Take care of unknown states. Fine. So this situation can happen both in melee and more FSM. Okay. Like suppose your more FSM has 6 states. So your melee always has one state less than more. So it will have 5 states. So if you do a 3-bit encoding, so it will go from 000 to 110. In this case, it will go from 000 to 101. So in both the cases, you have 111 and 110, 111. These are the states which are not at rest. So you have to specially take care of them. So output stability during state transitions is actually questionable. Okay, we have to additionally take care of them. Reduce state complexity. So that can be the answer. Like instead of having n states of more, we have n minus 1 states. Fine. So option D. So one of the ways in which you can make sure that the output is stable. See, the output is generally if you are making a so whenever there is a straight transition, your counter grows from suppose there is a 2-bit counter. It will go from 00 to 01, then 10 to 11. So in this case, you will see that here in this transition, 0 also changes from 0 to 1 and 1 also changes from 1 to 0. So this can lead to some glitches. So instead of this, we use gray coding. So that can make sure that only one state changes at a time. So that can be done for this. So moving on to the next question. Which of the following statements is true? R2R ladder DAC requires high precision resistors. Binary weighted resistor DAC conversion time is lower. And then we have binary weighted resistor DAC requires large range of resistors. And we have R2R ladder DAC is the faster conversion time compared to weighted resistor type DAC. So if you're confused, I can quickly go through the different kind of DAC. So this is your binary weighted resistor DAC. So you can see that the resistors are in the power of 2. Okay, so that only leads to the precision, bit precision. If you want voltage value to be converted into n-bit digital output, so you will have to keep n different resistors, each 2 times the previous one. So this is your binary weighted resistor DAC. The other one is R2R ladder. So this is a simpler one. So any guesses? Well, I will discuss the solution. So the option A says that R2R ladder DAC requires high precision resistors. So the answer is no. We only need R type and 2R type. In case of binary weighted, we need a whole range of it. R power 1, R square, sorry, it's 2R, 2R, 2 square R, which is basically 4R, 8R, all the way to 2 power n minus 1R. So the output value is highly dependent on the resistance of each one of them. Okay. Any slight variation, suppose instead of 2R, if it is 2R plus some delta, this is also 4R plus some delta. So the conversion will have huge variance. Okay. So we need high precision resistors in case of binary weighted DAC. Okay. Next is that, so binary weighted resistor DAC conversion time is lower compared to R2R ladder DAC. So these two statements are opposite to each other, right? R2R ladder DAC has faster conversion time. It means that the time is lower compared to weighted DAC. In this case, you have binary weighted DAC. Conversion time is lower compared to R2R ladder DAC. If you look at option C, so either B or D has to be correct. If you look at option C, binary weighted DAC resistor requires large range of resistors. So that is also correct, because in case of R2L, you need only these two, right? R and 2R. But in case of binary weighted, you need a whole range of them. You need n different types. Fine. So option C is correct. Now, I also did not notice that there can be two options correct here, because B or D are opposite to each other. Then one of them has to be correct. So in this case, I think that option B is correct. I'm actually not sure about this, because in both the cases we have a comparator and we have voltage input. So how can we determine the conversion time? So the option D is correct according to me. The reason is that option D is also correct. The reason is that if you go from R to R, 4R, all the way up to 2 power n minus 1 R. So as the resistance increases, the size of the resistor also increases. I need one page. Hmm. So let's look at this way. Initially we have R to R. In another case, we have R to R, 4R, 2 power n minus 1 R. So these are bigger resistors, right? So in case of bigger resistors, there is a possibility that we will have some parasitics. For example, there are many ways of making resistors. First is that you can use transistor in on state, or you can have big metal wires. So in this case, in case of big metal wires, what is the problem is that you have this metal wire, then you have silicon in your chip, then you have another metal wire. So this behaves as a capacitor. You have two metal lines very much close to each other, and then you have a silicon which acts as a dielectric, right? So this behaves as a metal oxide. This is actually silicon oxide. Okay. So it behaves as a metal oxide metal capacitor. And what is the another aspect of capacitor? You will have, if you make an equivalent model of this, your metal will have resistor, your downside, so metal below will also have some resistance, right? And you have capacitor, which can be modeled as like this. And when we talk about time, so one second. So when we talk about time, so what is the key thing that actually delays everything? That is the charging and discharging of the capacitor. because resistance do not offer anything, right? If you have, for example, this is your V input, here is your resistance, and this is your V output. Okay, so as soon as your V in is changed, V out will automatically change. But in case of capacitance, what will happen? As soon as you change your V in, there are charge occupied here. Okay, some charges will also be there. So as soon as you change V in, it will take some time for these charges to either charge up or discharge according to your V in. That will actually cause delay in your circuit. Okay, so is this clear? So in case of bigger resistance, what you have bigger metal lines, and these metal lines have silicon oxide between them. So it behaves as a metal oxide metal capacitor. So this is your equivalent model. This can look something like this. You have resistor chain, and you have capacitor, right? So these capacitors actually cause delay in your circuit. Your resistor cannot create delay. It will create delay, but it will be very much minimum as compared to the delay caused by capacitor. So that is the reason. So here you have bigger resistance, which will have bigger parasitic capacitance, and that will lead to delay. Fine. So in this case, we have two correct answers. First is that binary weighted resistor DAC requires large range of resistors. Okay. This one, and also R2R must be faster as compared to binary weighted. So is this clear to everyone? I think there is some couple of new concepts over here, like about parasitic capacitance. So should I move on to the next question, or if you have any doubt, you can ask. So I think I should move on to the next question if there are no doubts. So this was I was explaining the different kind of. I think I've explained the different kind of digital to analog converters. So in this case, depending upon your switching, we will have R by R plus R by 2R. That will give you your V out. So this is also done. So next question is that which of the following step is not present in analog to digital conversion process? So sampling and hold, quantization, encoding and decoding. So I will explain. So you have an input voltage, there is a switch, and there is a capacitor over here, and this is your ADC comparator. So your input voltage is actually changing with time, right? So you cannot continuously convert the input voltage to your output voltage. Sorry, the output digital value. Continuous conversion is not possible. I think in flash type ADC it is possible, but in other case you need some time. So to keep the input voltage as reference, you continuously. So you will what you will do is that you will switch this on. Okay, Vin voltage will be stored over here, and then you will quickly switch this off so that while you are doing the conversion, this input reference is not affected. Okay. For example, if your input voltage is 1 volt and you are converting it into a digital value, and suppose in middle of the conversion your reference voltage changes, then in that case your conversion cannot happen, right? Because your reference has changed. So it will only lead to error in your conversion. So that's why it is very much essential to sample and hold. So A is the correct because it is essential. Second is quantization. So as I explained earlier, you have two different voltage level. Suppose your V reference is 8 volt. So you have 8, 7, 6, 5, and your input voltage is 6.2. So in that case, what will happen is that if you pass this to a comparator, it will give you 1. This place it will also give you 1. In the upper case, it will give you 0 and 0. So the comparator cannot distinguish between 6.2 and 6, right? So it considers them, both of them, the same. So all the values from 6.0 to 7, they are basically equal to 6. Let me make it like this. Suppose this is your 8, this is your 7, this is your 6. So the conversion will look something like so. This is known as quantization. Okay. So in ADC, quantization is also a process. Next we have encoding. So we earlier, if you remember, we used a priority encoder to convert this value into the output, right? So we have encoding as well, but we do not have decoding. Okay. So the answer is D. Clear? So moving on to the next question, we have when will offset error occur in DAC, digital to analog conversion? So the options are when the slope of actual output deviates from the ideal output, when there is a constant offset between actual output and the ideal output, occurs when an increase in digital input results in decrease in analog output, and none of the above. So we have different kind of errors. So ideally, the slope should be 1. But if the slope is less, we call it gain error. Suppose the slope is correct, but we have something like this. So that is called as offset error. Okay. So in both the cases, we have here m equal to 1, which is the slope. In this case, this is m equal to 1 and this is m less than 1. So this is the gain error. Fine. So according to this, offset error occurs in DAC when there is a constant offset. When there is a constant offset. So you have the constant offset over here. So that causes the problem. So answer is B. So the next question is, what is the resolution of an 8-bit DAC assuming voltage reference is 1 volt? So in this case, let's discuss the solution. If you have a 8-bit digital to analog converter, which means that there should be 2 power 8 states. Fine. And those 2 power 8 states should lie from 0 to 1 volt. So the precision is 1 minus 0 by 2 power 8. So this comes somewhat around 39. So the answer is A. V max minus V min by 2n. N is bit. So the next question is that in a 5-bit successive approximation ADC with reference voltage of 1 volt, if an input voltage of 0.9 volt is applied, after 5 clock cycles, what is the content of SAR ADC? So a 5-bit successive ADC. So if anyone is trying, just let me know. I will wait. If not, then I will discuss the solution right now. So in a 5-bit successive, in a 5-bit SAR ADC, it starts counting from this position. The MSB will always be 1. Okay. So this corresponds to 0.5 volt. So first it will compare itself with your 0.9 volt input SAR output, SAR voltage, SAR output. Fine. So this is less than 0.9 volt. So it will update. So 11000. This corresponds to 0.5 plus 1 by 2, which is 0.5 plus 0.25, 0.75, which is less than 0.9. So update plus 11100. This is 0.5 plus 0.25 law is plus 1.25, which is equal to 0.875, which is less than 0.9 volt, which means update plus. So we have 11110, and this is 0.9375, which is greater than 0.9 volt. So it says -1. So 11101 +1 update -1 next +1, which is 0.90625, which is greater than 0.9 volt. So next we have 11 update -1 next +1. Okay, so this is the output. So the one we have used is 5-bit ADC. So we will have 5 comparisons, right? 5 cycles. So cycle 1, 2, 3, 4, 5. So after 5 cycles, we have 11100. So 11100. Option D is the answer. Moving on to the next question, we have which of the following element is not present in SAR ADC? Sample and hold, comparator, digital to analog converter, and inductor. So the answer is D, inductor. There is no use of inductor at all. Okay, and I think I have already explained the role of sample and hold, comparator, and digital to analog converter. Okay, so this makes sense. Next question is the conversion rate of a digital to analog converter depends on clock speed of input signal, settling time of converter, both A and B. So the answer is C, both A and B. The reason being is that clock speed of input signal. So in case of so here clock speed is mentioned. So by default it means SAR ADC. So in case of SAR ADC, what happens is that we have to keep on comparing. We have to update the value and keep on comparing with the input. Okay. So each comparison, it takes some time, which is known as your time period or clock cycle. Okay. So if we minimize it, then the comparison can be done faster. A lot of comparison can be done in the same time. Okay. So it definitely depends on your clock speed. The second is that settling time of a converter. So when you have this DAC, digital to analog converter, so it generated some VA voltage for comparison, right? Here you have your VA. Sorry, this is your V in. This is your V in. And you want to generate a VA for comparison. So you generated some VA, which will actually take some time to settle at VA. Okay. And then you will pass this through a converter, and that will give you the output 1 or 0. So in order to generate this VA, it comes from this digital to analog converter. So this also takes some time, right? If settling can be done faster, suppose the comparison happens at this point. Okay, because the output VA has settled. If the settling time is less, we can compare at this instant earlier. So overall, the conversion rate can be faster. Okay, so the answer is both A and B, clock speed and settling time of the converter. So I think that's all for today. If you have any doubt, let me know. I'm stopping the recording right now.